Friends, this is Dr. N. Athavan, working as an Associate Professor and Head in the Department of Physics at the Rajas College, Pudukkottai, a historical town in Tamil Nadu, India. In this video, I am going to show you the method of solving the Schrodinger equation of linear one-dimensional harmonic oscillator. Harmonic oscillator is a prototype to study the interaction between the radiation and the matter. As we know, matter is composed of molecules. These molecules have atoms in it. These atoms vibrate. These atomic vibrations are mostly harmonic in nature. The frequency of these vibrations fall under the infrared region of the electromagnetic spectrum. Hence, the harmonic oscillators are the more vital entities of the infrared spectroscopy. Thus, the problem of harmonic oscillator is considered to be the most significant one in the context of quantum mechanics. Here, there are two schematic representations are given for the harmonic oscillator. On the left, we have a vertical representation, and on the right, we have a horizontal representation. In both the cases, a body of mass m is fixed to one end of the spring of force constant k. The other end of the spring is fixed to a rigid support. This harmonic oscillator problem is well studied in classical mechanics. From the knowledge gained in classical mechanics, we write the potential energy of the problem as V of x is equal to half kx square. One can also write it as half m omega square x square. Before forming the Schrodinger equation of the problem, we write the Hamiltonian operator, which is nothing but the sum of kinetic and potential energies. P square by 2m is the kinetic energy and half m omega square x square is the potential energy. The general form of the Schrodinger equation is h psi is equal to E psi, where h is the Hamiltonian operator and psi is the wave function, E is the energy eigenvalue of the problem. By writing psi of x is equal to n into phi of x, where n is the normalization constant, and after the substitution of the corresponding operators for momentum and position, we get the Schrodinger equation as minus cross h square by 2m d square phi by dx square plus half m omega square x square into phi is equal to E phi. This equation is not comfortable, so we have to rearrange it. While rearranging, we get d square phi by dx square plus 2m by cross h square multiplied by E minus half m omega square x square into phi is equal to 0. Now, one can easily simplify this equation by defining a new variable xi is equal to alpha x, where alpha is equal to square root of m omega by cross h and a new parameter lambda, which is equal to 2e by cross h omega. The differential equation takes the form d square phi by d xi square plus lambda minus g square into phi is equal to 0. This is the equation in question, which has to be solved subject to the admissibility and boundary conditions. The admissibility conditions are: the solution has to be continuous throughout the region concerned, its derivative also continuous. At the boundaries, the solution should vanish. This DE is very hard to solve, so one has to assume a solution of the differential equation as a product of two continuous functions, out of which the first function will take care of the boundary conditions. The best choice one can have is the exponential minus z square, and the second function can be expanded as an infinite series, provided the series does not violate the boundary conditions. The boundary conditions here are phi at plus infinity and at minus infinity should vanish. This has to be satisfied. We write the phi of z as e power minus z square by 2 u of z. In this, e power minus z square by 2 will take care of the boundary condition, that is phi of plus or minus infinity is equal to 0 because e power minus infinity is 0. Here the coefficient of the z square in the argument of exponential function, that is half, is inserted for convenience. This will be useful when we determine the normalization constant. Another function u of z, which is going to be expanded as an infinite series. So after the substitution, we get d square u by dc square minus 2z into du by dc plus lambda minus 1 u is equal to 0. As we said before, we are going to try for a series solution as follows. So we write u of z as summation running from r is equal to 0 to infinity a r xi power r. Therefore, du by dc takes this form and d square u by dz square is given like this. Substituting expressions for these two derivatives in the equation, we get this final form. As the right hand side of this equation is 0, one can collect the coefficients of each power of z and equate them to 0 as below. For that, we have to put r is equal to 2 in the first and r is equal to 1 in the second term and r is equal to 0 in the third term for equating the powers of xi power 0. Similarly, xi power 1, xi power 2 can be written like this, and the coefficient of the general term xi power n can be written as n plus 1 into n plus 2 into a n plus 2 plus within bracket minus 2n plus lambda minus 1 into an, which is equal to 0. As the right hand side is 0, we can write an plus 2 by an is equal to minus 2n plus lambda minus 1 divided by n plus 1 into n plus 2. For any infinite series to converge, the condition, that is, as n tends to infinity, the ratio of successive coefficients should be very, very small, or in other words, they should be infinitesimally small. As n tends to infinity, an plus 2 by an for our case is going like 1 by n, which is not acceptable because this has a similarity with the series expansion of the function e power xi square. Therefore, the total function phi of z as z tends to infinity, which violates the boundary conditions, because at the boundaries phi of z should be 0. So what one has to do is terminate the infinite series at some point. That means after some terms such that the ratio an plus 2 by an is equal to 0. That is, u of z is now made as an polynomial of degree n. This results in the condition that minus 2n plus lambda minus 1 is equal to 0, or in other words, we can write lambda is equal to 2n plus 1. Once we get the condition on the lambda, which contains the energy eigenvalue, we can immediately write the energy eigenvalue as E is equal to n plus half h cross omega, where n is an integer which runs from 0. So the energy eigenvalue E can have only discrete values. That means we have a discrete spectrum of energy here, or in other words, the energy is quantized. Moreover, the lowest energy value in our case is half h cross omega. So this is a new result. In classical mechanics, we get the lowest possible energy as 0, but in quantum mechanics, the lowest possible energy is not 0, but half h cross omega. This half h cross omega energy, we term it as 0 point energy. So this 0 point energy manifests that we have oscillations even at absolute 0. As we do not have such a non-zero lowest possible energy in classical mechanics, this new result is considered to be a special feature of quantum mechanics. Also, the energy levels are equally spaced. That means they are looking like a ladder with a difference between two consecutive levels, which gives us the value h cross omega. Next, our job is to find the eigenfunctions of the problem. For finding the eigenfunctions, we substitute the value of lambda in the differential equation. We get d square u by dz square minus 2z du by dz plus 2n u of z is equal to 0. This differential equation is similar, or this differential equation is looking like the Hermite differential equation. Therefore, we can immediately write Hermite polynomials are the solutions of this differential equation. As n refers to the quantum level, we write u of z as un of z, which is equal to hn of z, where hn of z is the Hermite polynomial. Substituting the value of un of z in the definition of phi of z, we get the unnormalized eigenfunctions as phi of z, which is equal to e power minus I square by 2 hn of z. Now the normalized wave function in z is psi n of z is equal to n into phi of z. Previously we said this n is nothing but the normalization constant. So the remaining job is only rest with the finding of normalization constant n. This is the general normalization condition. Integral from minus infinity to plus infinity psi n star z psi n z dz is equal to 1. That is n square e power minus I square hn square xi dz is equal to 1. We can immediately write the value of n as 1 by square root of 2 power n factorial root pi, because we know that the orthonormal condition of Hermite polynomials gives us the value of the integral as 2 power n factorial root pi. Substituting this in the definition of psi n of x and reverting to the original variable x, we have the wave function for the harmonic oscillator, which is nothing but psi n of x is equal to root alpha divided by square root of 2 power n factorial square root of pi into e power minus alpha square x square by 2 hn of alpha x. Here we give you some of the ground state and few excited state wave functions. Now the problem is completely solved, which means we have the eigenspectrum En is equal to n plus half h cross omega, and the eigenfunction or the wave function psi n of x, which takes the form given here. In another video, we present you the solution for harmonic oscillator by using ladder operators. Those who are interested may have a look at it. Thank you for watching and learning.